Hi boys and girls, let me wholeheartedly invite you to this semester's course, that is uh, Logic Circuit Design, ECT203 Logic Circuit Design. About this course is a very simple course. This paves foundation for digital design, which has a lot of scopes. And in this we tell you the basics of Verilog, which gives you a tool which gives you cutting edge in the VLSI job market. So this time it is due to the COVID, this composite class. I think both batches of electronics and communication as well as the instrumentation students are there. For all of you, this course will be very beneficial. So let me start with this presentation. So the speech is organized as the learning outcomes from this hour, and the course outcomes in your syllabus, then the overview of this course, then about the linear systems and the digital systems, then binary and hexadecimal number systems, and summary of what you learned. So in this video you will understand the course outcomes, and this actually copied from the syllabus. I shared the syllabus with you. Hope you have gone through that syllabus. And in this thing, there's a lab also associated with that. There's something called the Logic Circuit Design Lab, as well as there's a mini project for this paper. Hopefully we can meet in the labs, etc. in December, at least in December. And you will learn the need for logic design. Then you will learn the need for using some simulator like a Cube. So I will be using a quite universal circuit simulator in this semester. So I strongly recommend that all of you have a computer, preferably a laptop, in which there's an installation of a quite universal circuit simulator. And we will teach you about Verilog this semester in this paper, because last time these things were not included in your syllabus. So this time we purposefully included Verilog design in the third semester itself, so that by the fifth or sixth semester you will be very familiar with the digital design. So Verilog gives a lot of job opportunities. There are a lot of job opportunities in the VLSI and FPGA segments, FPGA job market. So this is very important. Verilog is very important. So then again you will review the sphere of opportunities, which we discussed in the previous semester, at least for the AA batch. Then you will learn the binary and hexadecimal system and contrast them with the decimal system. Then you will learn the conversion among the different number systems. So course outcomes, first is you will learn, the student will learn to explain the elements of a digital system abstraction, such as digital representation of information, digital logic, and Boolean algebra. So these are very important things. We will start with number systems and the Boolean algebra, and based on that Boolean algebra you can develop digital logic, and based on that digital logic circuits you can develop digital systems. So then you will create this course will create an you can create implementation of a combinational logic circuits using gates or multiplexers or something. Then you compare the different types of logic families, like the TTL logic family, the CMOS logic family, and you can compare them. Then you will design a sequential logic circuit with basic building blocks like flip-flops. There is another kind of digital logic circuits you will learn. Then you will design and analyze combinational and sequential logic circuits using gate level Verilog model. This Verilog is very important. This part of is very important. You have to understand Verilog very thoroughly, because you get a lot of opportunities in Verilog. So the sphere of opportunities, if you say the sphere of opportunities, this diagram I discussed in the previous semester when I taught you the C programming. So this diagram I am reviewing now. In the last semester I told you whatever I put in blue, you have to pay attention to this part in blue. This is meant for computer science students, and this blue part is meant for all electronics students. So you have to you have to learn whatever I have put in blue. You will have to understand very thoroughly when you pass out of this course. So in the last semester, I told you about the general computing languages, and I told you about the C programming. I told you about C programming. C++ you will have to learn as you wish. And if you learn these things, you can go into embedded software development and IoT device and all that. And this also I taught you in the previous semester. I don't know how many of you understood it properly. The language for documentation. No one gave a documentation in LaTeX. Only one student or two gave a documentation in LaTeX. But this is very important. So at least this semester you go through this LaTeX part and do the leaks. Once you know LaTeX, you may not be needing leaks. So languages for documentation, this is very important. The publishing part, representation of reports, representation of your ideas as reports or presentations, etc. This is very important. And if you come here, the languages for scientific computing, this semester you will have to learn Python. I strongly recommend that you go to some minor classes, a computer science minor or other minors, and learn more skills and acquire more skills than you get from our own department, than your parent department. Go to other departments, take these courses, and gain as much skills as possible. Now here you have a lab in this semester that is called the scientific computing lab. Make sure that you do it in Python, so that you get acquainted with Python. Python is very, very useful. So if you learn Python, you can do many things in machine learning, artificial intelligence, etc. All these things will be affecting the communication industry very soon. So at that time, don't be at a loss. So you learn this Python and ML AI, make an introduction to ML AI, at least learn Python this semester, so that you can learn these things later on, so that when a new era of communication revolution happens, you don't fall behind. And if you come here there is a hardware description language in which we will teach you very long this semester. VHDL you can learn on your own later. So then you will see the implementation FPGA, etc. So this semester you have another lab, that is a digital logic design lab, where you will be half of your experiments are based on Verilog and something called a tiny FPGA. So I strongly recommend that these tiny FPGAs are usually very cheap, maybe around 1,500, 1,800 you can get a tiny FPGA, lattice boards, etc. So I strongly recommend that you purchase one board, maybe as a group. If this amount is too big for you, then you can purchase as a group, and you can do these simulations and these implementations at home itself. So due to especially in the COVID situation, you don't fall behind in your labs. So the labs are very important. The skills are very important. So I strongly recommend that you buy a tiny FPGA and you do this Verilog and implementation in FPGA at home. And in your computer itself, you can do this Python coding. These things are very important. The Verilog part and the Python coding are very important this semester. So this semester itself, you will get a lot of skills. So what is the need of the logic design? Why should you learn this paper? If you look into modern communication systems, instrumentation system, medical instrumentation, control device, they are all based on digital logic and digital circuit. So you have to learn this. So if you go to a hospital, you can see the whole device, all electronic devices, they are all digital devices. If you look at the patient information system or patient surveillance system, or if you look at a MRI machine, or if you look at the EEG machine, you can see all digital systems in play there. So you have to know about digital circuits. And binary circuits based on Boolean algebra, they form the base of modern digital logic. Modern digital systems, they are based on binary circuits and Boolean algebra. So it is mandatory that you learn Boolean algebra and digital circuit design and implementation very well. And the tools I use in this semester, in the syllabus we have put only open source tools, which a student can download and install in his home machine, and you can play around with it. One tool that I use is a Quite Universal Circuit Simulator, or QUCS, QUCS. It is used for digital demolition. Actually, it's a high frequency circuit simulator which you can use for high frequency circuits, as well as low frequency continuous circuits, as well as for digital circuits. So this is a very handy tool which you can download and install on your machine. This is something running on NGS Spice language. So it's a very convenient tool. You can draw pictures and you can simulate them. You can see verify your designs with open tools. You can verify your design with the help of waveforms or truth tables or graphs or charts or whatever. And Verilog, that will be used for simulation and synthesis. So I strongly recommend that you install iVerilog, something called Icarus Verilog, and what you call the GTK Wave, and Icarus Verilog. I will come to that. I will come to all those tools when we discuss Verilog. So we will be using Verilog and Qt. So knowledge of Verilog will give you cutting edge in the VLSI job market. This is very important. It is in the VLSI field that you get the largest amount of payment. So you can start with salaries as high as 15 lakh a year. So you can, even starting salary will be around 15 lakh a year. So maybe they will not recruit you directly to Intel from CEC. Maybe if you are fortunate, good. Or else you can try companies like Cadence, then what do you call, what do you call, Synopsys or such companies, and then you can target much bigger companies. But Verilog is mandatory. VHDL is also good, but start with Verilog. And if you say about the linear systems versus digital system, this slide actually lacks a little precision, because somebody who knows signal processing, linear digital signal processing, etc., may frown upon some of these ideas. I purposefully made it a very primitive slide. So linear systems like amplifiers, analog filters, etc., work on continuous signals. Actually, they are not linear systems. There are some non-linearity, but I assume the linear operation of the amplifier, or linear regions only. So they work on continuous time signal. So what is a continuous time signal? A signal like this is a continuous time signal. This is actually a full wave rectified signal. So if I take any arbitrary time interval, if you look at the signal, you can see that this signal has got infinitely many values during this small delta t. Comparing with a digital signal here, if you say digital signals are actually discrete versions of a signal, that is either it is a high or a low. So here this is a signal that is high for say a 2 duration, then it comes down low for some duration, then high for some other duration, another 3 time durations it is high, then again it goes low, and again remains a high. So if I take an arbitrary time interval, you can see that it has only a finite number of values. Like this is a 0, here this value is a 0, and here it is a 1. Okay, so such a signal is called a digital signal. In fact, strictly speaking, this is also a continuous time signal, because the time axis is continuous. But for the sake of ease of your understanding, I take it as a digital signal. I assume that this width is very small, so that this looks like an impulse. So this is high for say, so this is representing the bit pattern 101101. So this 1 may be represented by a 3 volt, and a 0 may be represented by a 0 volt, again a 3 volt, 3 volt, 3 volt, then again a 0 volt. Okay, it can be a 3 volt or a 5 volt. Standard it is a 3 volt. Sometimes this low may be represented by a minus 3 volt, depending on the type of circuitry you are using. So digital signals have discrete time axis and can have a finite number of values in small time intervals. So here if you say these are zeros and 1, so this is a binary signal, and this is a continuous time signal. So those systems operating on these digital signals, they are called digital systems. Yes, and this number system you have to understand. Probably you learned in your school classes this humans operate with a decimal system. This decimal system of numbers is invented by Indians, although the Westerners call it the Arab numerals. Actually, Arabs got from India. So this is an Indian system of decimal system. This uses 10 symbols 0 to 9. Then they are used to represent numbers with periodicity 10. Like I have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then after 9 you say a 0 with a 1, 0, which you call as a 10. 10, 11, 12, 1, 0, 1, 1, 1, 2, which you call as 10, 11, 12, 13, that way, 1, 9, 19. And then again you see zeros, that is a 2, 0, 20. Likewise, so every digit gets repeated after 10 clock cycles. So after 10 numbers gets repeated. But digital systems work with a binary number system, because digital systems cannot work with this decimal system, because I cannot have systems that have 10 states. So 10 decimal system means I have to have 10 states for the system. That is not possible, because most digital systems operate with the help of switches, solid state switches. So the switch can be either off or on. So it is wise to use a binary system where a switch is either on or off. Where if the switch is off, it is treated as a 1, or if it is on, it is treated as a 0, or otherwise. So it is a convenient system as far as the switches are concerned. The binary system is very convenient. Although humans cannot easily understand, the computers can easily understand that. So the binary system representation becomes very important. And then we use a hexadecimal system also, because humans cannot easily interpret this binary number. So a hexadecimal systems come as convenient, because you can easily convert a hexadecimal number into a binary number, and a binary number into a hexadecimal system. And a hexanumber decimal system can be remembered, like a hex number can be remembered by us, and it can easily convert to binary system. So it's very convenient and in vogue with binary. So hexadecimal system means its base is 16. So you have symbols from 0 to 15, and they get repeated after 16 numbers. Now if you look at the binary and hexadecimal numbers, see, this is a decimal system. There is a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. After that this repeats 1, 0, 1, 1, 11, 12, 13, 14, 17. I have written only up to 17. Okay. And if you look at the binary, it cannot exceed 2. It cannot exceed 1. 0, 1, there cannot be a 2. Instead, like I have 10 here, I have a 1, 0 here. This is not a 10, it's a 1, 0 in binary. Next is a 1, 1. Then again two numbers are over. So it next becomes a 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. This is 8. Okay. Then 1, 0, 0, 1 is 9. 1, 0, 1, 0 is 10. 1, 0, 1, 1, 1, 1, 0, 0. That is 12. 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1. Then I have a 16. That is 1, 0, 0, 0, 0. 1, 4 zeros. Then 1, 0, 0, 0, 1. Okay. Now if you, so this is how the binary system goes. If you look at the hexadecimal system, there are 16 symbols. There are 16 symbols. So it starts with a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But 9, after 9 I have a problem, because I cannot write 10. Because then there will be tremendous confusion whether I am writing a 1 or whether I am writing it as a 10 or is it a 1, 0. There is a problem, because this symbol, this 1, 0, this will conflict with this symbol 1 and this symbol 0. So conveniently, instead of 10 I write A. Okay, symbol A is used. A is 10, 1, 0, 10. 10 in hex, hex in A in hex means a 10 in decimal. Okay, so this 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. Okay. After F comes 16. 16 is nothing but, like I have 1, 0 here, like I have 10 here, I have next number is a 1, 0. This is a 1, 0. This 1, 0 is nothing but 0 into 16 raised to 0 plus 1 into 16 raised to 1. That is a 16. We will come to this conversion. Next will be a 1, 1. Next will be 1, 2, 1, 3, etc. Okay. So this is how the decimal and decimal, binary and hex numbers do look like. Now this conversion from decimal to binary and hex is pretty straightforward. Probably you learned in your school classes. So if I have a decimal number like 1000, what I do is I divide by 2. I repeatedly divide by 2, and I take these reminders. Okay, these reminders form the bits for my binary number. Okay, so 2001 divided by 2 gives a 500, so that has a remainder of 0. They again divide by 2, it's a 250, remainder is 0. Again divide by 2, it's a 125, it's a remainder is a 0. Then you divide by 2, it becomes a 62 with a remainder 1. Now this division is not full, so there is a remainder 1. So you divide again by 2, that's a 31, so the remainder is a 0. Again you divide, it is a 15 with a remainder 1. Is 7 with a remainder 1, then again 3 with a remainder 1, there's a 1 with a remainder 1. Okay, so there's a 1 with a remainder 1, 1 with a remainder 1. So what happens is I write in this manner 1, 1, 1. I write in this manner 1, 1, 1. There are 5 ones. Okay, there are 5 ones, 0, 1, 0, 0, 0 to the base 2. You can do a couple of exercises and you can verify this. And to hex is pretty simple. Instead of dividing by 2, all you have to do is divide by 16. I divide 1000 by 16, it becomes 62 with a remainder 8. So 62 when divided by 16 gives a quotient of 3 and a remainder of 14. Okay, so 3 cannot be divided by 16, so that comes as a remainder. It's a 3, 14, 8, but 14 is represented not as 14 but as E. Okay, so the number is 3E8. 14 is E. If you look here, 14 is E. Okay, 3, 8, 16. But once you get this binary, between binary and hex, it is a pretty straightforward conversion, because what you have to do is, this is a binary number. For converting to hexadecimal is very easy. If you look at 4 digits, 4 bits. 4 bits are called, a collection of 4 bits is called a quad. So you look at the first quad, it is a 1000, which is an 8. This comes here as a first least significant thing. For a binary number, this is called the least significant bit, because this is the least significant, smallest significance, and this called the least significant bit, or LSB, least significant bit. And this is the most significant, because if it changes, the value changes drastically the value changes. If this changes to 1, no serious change will happen in magnitude. But if this changes, the value changes considerably. So this is the most significant bit, or MSB. So the first bit is called MSB, or most significant bit, and this is the least significant bit. So if I take from the least significant quad, it's a 1000, that's a 8. And next quad is a 1110. From here to here, 1110, which is nothing but E, nothing but 14. Then the next quad is, there is no quad, only a pair is there, 1 it is actually 0011, which is 3. So this is 3, 8. If you have to convert from here to here, straight away write the quads, like 8 is 100, and E is 1110, and 3 is 0011. So it becomes 0011, 1110, 1000. So this is how the conversion between decimal to binary and hex, and the conversion between binary and hex to binary, it is pretty straightforward. And what if you have a decimal point also? In decimal point part, you have to do multiplication rather than division, that's all. If you have a point like 1000.47, 1000 part, you know, the binary part, you know, you have just computer, and 0.47, the decimal part, the binary part corresponding to 0.47 need be computed. What you have to do is, you repeatedly multiply rather than dividing, because it's a fraction part. You multiply by 2, so that 0.47 when multiplied by 2, it becomes 0.94. Look for this part, this is a 0, that implies a 0. So the first bit is a 0. 111, whatever this 1000 part, 0.0, first is a 0. Then you 0.94, you multiply by 2, so that it becomes 1.88. So this 1 comes here. Okay, this 1 comes here. And 0.88 you multiply by 2, again it becomes a 1.77. This implies a 1 here. Okay, so next is a 0.76 into 2, that's a 1.52. This 1 comes here. So 1000 in hex, if you look at this number, 1000 in hex, if you say it is 3816. So 0.47 you multiply by repeatedly by 16. So this is how I do the conversion into binary. This is a conversion to hex. So here earlier you multiply by 2, here you multiply by 16, so that 0.47 when multiplied by 16, it becomes a 7.52. So this is 38, 1000 part is 38, then followed by a 7. Then 0.52 is taken, that is multiplied by 16, that becomes an 8.32, so this 8 comes here. This 0.32 is multiplied by 16, this becomes a 5.12, so it becomes a 5 comes here. So 0.12 multiplied by 16 gives a 1.92, so this 1 comes here. This is how the decimal part, that is a fractional part, is converted to both binary and hex. Now what about the reverse conversion? It is straightforward, binary to decimal. All these are to be multiplied by the integer part has to be multiplied by corresponding powers of 2 and added up. The fractional part you have to multiply by powers of 2 raised to minus negative powers of 2 and then add up. Like this 0 into 2 raised to 0 plus 0 into 2 raised to 1 plus 0 into 2 raised to 2 plus 1 into 2 raised to 3 plus 0 into 2 raised to 4 plus 1 into 2 raised to 5 plus etc. Plus what? I have to have the negative powers. 0 into 2 raised to minus 1 plus 1 into 2 raised to minus 2 plus 1 into 2 raised to minus 3 plus 1 into 2 raised to minus 4. So when added up, it comes to about 1000.4375. You have to check it out. Please do this computation and see whether I have made any mistake. It doesn't completely come to 1000.47 because I took only up to this point. Please check out this computation. And hex to decimal, it is pretty straightforward. Like you multiply by 8 into 16 raised to 0 plus e is 14 into 16 raised to 1 plus 3 into 16 square. Okay, so that is about the integer part. Now the fractional part is 0.7851. You multiply by powers of negative powers of 16, so that it is 7 into 16 raised to minus 1 plus 8 into 16 raised to minus 2 plus 5 into 16 raised to minus 3 plus 1 into 16 raised to minus 4, so that it becomes 1000.4687. You can verify that. So this is how the conversion between hexadecimal binary to hexadecimal, hexadecimal to binary, binary to decimal, decimal to binary, between binary and hex to binary. That's very simple. So what you understood in this is you understood the course outcomes, then you understood the significance of logic design, what cutting edge it gives you. Then you learn the names of software tools, namely QX and Verilog for simulation and synthesis. And this Verilog is a very important part which you have to learn very thoroughly, so that improves the cutting edge in the job market. You reviewed the sphere of opportunities we discussed in the previous semester. So why we learned these computational tools, so how far you have learned and what more is there to learn. You learned the binary and hexadecimal system and you contrasted them with the decimal system. Then you learn the conversion among different number system. So you do some more exercise at home and you understand this conversion very thoroughly. And that we come to the end of this presentation. I thank you all.